All right, we waited for long enough, 4 minutes after the hour. It's our great pleasure to have Adam Bates here, professor from Yuile, UC. Adam has been doing security for how many years? More than me or less than me?
I think I'm a little bit less than you.
Okay. So only 10 years?
Well, you were trying to hire me last time I visited BU, so I must be a few years younger than you, right?
Yeah. Well, it depends.
Right. Maybe that's a little bit overly optimistic that you were trying to hire me.
Let's not count. He's way more successful than I am, but he has awesome work to talk about. So don't shout bingo. I guess that's instructions for the talk, or do we shout bingo during the talk?
We'll see.
Do we shout bingo when we want to ask you a question?
Justified in one slide.
Do you want questions during the talk or only at the end?
You can talk. You can have questions whenever you want.
All right. Sounds good. With all that said, Adam, take it away.
I don't know how to get rid of this. This meeting is being recorded.
Okay.
I'll do that. Find my second display here. Oh, there it is. All right. Thank you. Maybe that wouldn't have bothered anybody but me, but I'm feeling much better now. Hi, everyone. So excited to be here. I am getting over a cold, so apologies. Of course, I've got a preschooler at home. By getting over it, I mean maybe by April I'll sound better. Thank you so much for being here today. So, quick update. We are still awful at preventing data breaches. Every time I need to give a new talk, I go to old reliable information.beautiful.net. They've got this tracker for the world's biggest data breaches. And if anything, the breaches are only increasing in frequency and scale. The things that probably looked really catastrophic in 2018 now don't even warrant any text here. It's bad. And it's easy to become desensitized to the consequences of these incidents, but they're actually vast and affect far more than companies' bottom line. There's numerous instances of these types of incidents having real measurable impacts on people's financial well-being. We've now seen numerous incidents where data leaks and penetrations were weaponized for political gain, as well as consequences for national security, SolarWinds, Office of Personnel Management. Yeah.
Were there any non-trivial consequences for any of these data breaches?
Were there any non-trivial consequences?
Did someone get fired, lose money?
Yeah. So I mean, certainly there's frequently heads rolling
because of the data breaches.
So you're suggesting that?
I'm suggesting the reason we have them is because there's no actual consequences. So.
That sounds like a completely separate talk, unfortunately. I was planning on giving.
Okay, never mind.
Yeah, no, certainly I think there's plenty of instances where, plenty of folks hang the 2016 campaign on the, effectively, non-result of the emails with the DNC, right? So I think that there are severe consequences. Sometimes it can point to loss of data, of money, certainly loss of employment in some cases. In other cases, the consequences are more severe. But then, if we're being cynical, this is my obligatory, the things that I do matter to the real world slide before I pivot to things that are far more niche, right? Okay. All of those bubbles were right before the advent of adversary use of generative AI. So things could be getting much worse. There was a abuse report put out by Anthropic over the summer, and one of the things they wanted to tell the world about was that cyber criminals were using one of their models to generate ransomware. And in particular, this wasn't sort of, an industrious hacker trying to accelerate their work, like a healthy little co-pilot. This was someone who didn't have the technical means to develop malware, was able to generate and sell malware with the use of generative AI. So what this tells me is that, the capabilities of what we think of as sort of like nation-backed advanced persistent threats today could become the baseline capabilities of novice script kiddies tomorrow. Yeah.
Have you seen Google's press release from yesterday on exactly this topic?
Oh yeah, was there another one?
Well, they looked at all this stuff, they figured out all of it is bogus, and the case that they were talking about is Ramesh Kari with his research group trying to figure out
seriously?
what was going on. So next time you give the talk, you can add one more slide to this.
Hide that slide. Thanks very much. Okay, hard pivot. This is going great. So how are we trying to mitigate and defend against these threats today? What are security operations centers doing to detect and repel these attacks? So our basic detection model is based on, we install sensors everywhere to generate these streams of telemetry. And a lot of the work that you might be doing in your lab involves use of highly sophisticated neural networks and anomaly detection, etc. This preoccupies the imagination of the academic community. No, we're not really doing that. Instead, all of these telemetry streams are compared to a set of handbook detection analytics that some analysts wrote down, maybe in response to reviewing some threat intelligence, to try to detect some particular threat behavior. And if there's a match, then we're raising the alert. So effectively, we are deploying very, very sophisticated regular expression engines as our primary means of detection.
It's like virus scan just for the.
Well, virus scan is, I guess potentially, yeah. So antivirus is, maybe at one level above, sort of like traditional antivirus in terms of sophistication, because we're not necessarily matching against strings of bytes in order to do the detection. There is some sort of analysis of the logic of the malware, of the adversarial behavior.
So there's memory.
Yeah, institutional memory effectively is what we're sort of codifying in these systems. And here's an example of one such threat detection analytic from Carbon Black. We can see here sort of the raw detection logic, which is basically just whenever we see cron do anything, fire an alert. And one of the nice things about this, as I dunk on it a lot during this talk, is that it is intrinsically explainable, right? Because someone sat down and wrote this, we have an explanation for why the alert exists. We're able to say, okay, on a scale of 1 to 10, here's the severity if this detection goes off. And then we also have all of these annotations to help us further make sense of the detection. In particular here, some of these tags are attributing this low-level behavior to different concepts in the MITRE ATT&CK conceptual framework. So in this case, we know that the behavior is related to adversarial execution of code. And in particular, if we looked up technique 1053, we see that's related to scheduling, adversarial scheduling of tasks and jobs. So these systems are extremely noisy. False positive rates can exceed 75% on these products, even when they're properly configured, which brings us into investigation. So we have this extremely noisy alert stream, and it's essentially analysts' jobs to examine the detections that are coming out of this alert stream. Maybe we're trying to denoise them a bit by correlating multiple alerts together in the hopes that we can identify suspicious patterns. At the end of the day, though, the problem reduces to manually querying raw events to confirm the threats, and then use the results of that investigation to plan some type of response. So additionally, we have this problem on the human capital side, where there's high rates of burnout in security operations centers. There's cases where just sort of the fatigue of performing these tasks causes true detections to go uninvestigated, and overall just a wide consensus that we there's a pipeline problem in terms of connecting with the skilled practitioners that we need in order to do these jobs. So my biased perspective on where these systems are falling short, one is a lack of context. So all of these threat detection systems have the memory of a goldfish. They're issuing these detections per process, per device, sort of atomically, completely in isolation, without regard for anything else that's going on. Every single process is a detection. We move on to the next process, no understanding of how those processes interrelate. And we saw that the vast majority of the work was really happening between the ears of the human analyst, because we're not good at reliably detecting threats. We're not even good at accelerating these investigations. human cognition is doing most of the work here. And then finally, here's my reference to our title, right? I've done a lot more, engaging with stakeholders over the past couple of years, and a lot of times we're surprised to hear their perspective on these shortcomings. By no means is this the perspective of every single person that works with these products. A lot of times they think the products are actually doing a very good job. I think one of the reasons for that might be that the way that we're reasoning about assessing the quality of these products, and by extension, the security readiness of these organizations, is kind of based on flawed ideas about how the products work. Today, I'm going to be sharing sort of two veins of work that we're working on. The first, we'll try to directly combat this issue of signal-to-noise ratio in the threat detection products. And I'll show you that by providing additional context, by moving away from that memory of a goldfish model, and by examining the history of these alerts and understanding why they came to be fired on the system, we can actually predict the veracity of the alert. And then secondly, I'll show you that metrics based on that admittedly highly valuable and useful MITRE ATT&CK framework can actually obscure rather than illuminate organizations' security readiness. All right, first up, the history of an alert predicts its veracity. This work was done with my student, Oji, as well as a bunch of folks at NEC Labs who have now left NEC Labs, but for clarity, since we're using some of their products, I've used their former affiliations on these slides. So a lot of my work in this space draws on this concept of data provenance, which examines the suspicious activities based on their historical context within the system. What is data provenance? Well, effectively, what we're going to do is define a parser that examines the streams of event telemetry and then turn this into a causal relationship graph that surfaces the interdependencies between these different events. So as we can see here, each event describes an operation performed by a program on some other object within the system. These programs and objects become vertices within a graph, and the events become edges describing the relationships between those entities. This couldn't be more straightforward, yet in contrast to this existing system where everything's kind of examined in isolation, it's a dramatic change. So why is that? Let's say that this event here causes an alert to fire. Effectively, even in this toy example, an analyst might need to issue 1, 2, 3, 4, 5 different queries based on the context available at each point in order to identify a root cause associated with this alert. In contrast, by examining the provenance graph, we can see that this relationship between the alert and its root causes is structurally represented within the data structure. Yeah?
How do you create this graph?
Yeah, kind of fun animation about it right here. So essentially, we're just defining a richer, more semantically deep parser, kind of an analog between like firewalls and deep packet inspection. Like we're delving into the structure of the events more than the existing systems. But essentially, every single event is defined by a source, a program object, and access tuple. And so those cleanly map to a source vertex, a destination vertex, and an edge type.
Yeah, how do you determine the edges? That's what's not clear to me.
Yeah, so for take this netcon event, Firefox triggered a netcon event connecting to this IP address, maps to a Firefox vertex, having a netcon relationship with this IP address.
Oh, I see. So you're taking each triple there and enclosing it into the graph.
Yep, yeah. I'll be skipping through a couple of animations here. Pardon me. There we go. Talk analysis, it's great. And then, another thing that might make this provenance analysis very powerful is that it also allows us to see not, spurious correlations between these alerts, but causal relationships between these alerts. So we have a much stronger foundation with which to analyze. So why would the provenance of an alert? Yeah, go ahead.
Just sticking to the simple example here where Firefox connects to this IP address,
Firefox is the thing that will connect to dozens and hundreds of IP addresses at the same time, more or less. Where you would probably get a pretty big fan out on this netcom there.
Yeah, 100%.
And you don't know in advance what where the attacks are.
And I was grappling with whether or not I should extend this sequence to say, by the way, here's why what I do is hard. And I opted not to, and this might be the feedback I need on that. So yeah, one of the things that makes this challenging, makes it an active area of research, is effectively we've got a semantic gap problem. So all of these processes have these rich internal representations of what's happening. For example, Firefox has multiple browser tabs open, but we're doing our monitoring at the operating system level effectively. And so it's not always clear from these, system call logs or endpoint event streams what the actual information flow relationship is with the above systems. So a lot of the work that I've done have, come up with efficient ways that we can maybe enrich this event stream in order to do something better. What we're going to be focusing on here is actually an even worse case of this problem, where the logs aren't even as high fidelity as system calls. So commercial endpoint detection and response tools use these much coarser grained events. So for an example, like with Firefox connecting to this IP address, we don't actually get a new event every single time they write something to the socket, which could be useful for us if we needed to delineate the sort of interleaving of multiple events. Instead, we just have one event that says Firefox did this once. Yeah.
It's worse. You're also interleaving things that might not actually be related. Like you might have, you might have an edge from, I don't know, an IP address to Firefox, another one from Firefox to another IP address, but that,
Yeah, and it might not even be a single hop relationship, right? Like it could be that, I have a dependency 2 hops away that all of a sudden read a new file, and now it has, the internal state of that program represents a new information flow. So if I write again, it means a different thing than I did previously. Exactly. It's not necessarily clear.
So you don't necessarily have causal.
Yeah. So for the stuff I'm going to be presenting today, in spite of that infidelity, we found that it doesn't matter. Is the exciting part, right? So that's the good news. I'm not necessarily going into every low-level result in terms of how we do the traversal today, but I'd be happy to talk about that after the case as well. Instead, what I wanted to do is give us a high level of why analysis of these graphs would be helpful in determining whether or not this is a true alert or a false alert. Our first effort was sort of based on this idea that, some histories are more suspicious than others. For example, in this particular graph, a number of the edges that I'm showing here kind of represent very common events. Firefox is this plugin container helper process to Firefox is always going to contact services. Same for LSASS. Firefox is always going to launch its audio driver, which is going to connect to service hosts. Whereas some of these events are far less frequent and are more likely to indicate something suspicious. So if we could somehow take this, aggregate this notion that some events are common, some events are less common, and attribute all of that to the alert, maybe we could use that as a way to triage the alerts, determine which ones we should look at first. So in this first, this paper that appeared in ESS 19, for each path in this graph that's comprised of a set of events, we calculated the probability of this source connecting to this destination over this relationship, and then basically took the product of all of these probabilities. So if you can understand this idea, essentially every single edge is assigned a weight based on its frequency or probability, and then we mush them all together to produce a score for this value. Then you've got the high-level idea.
This assumes no dependence.
Sorry?
This assumes no dependence, right? You can't just multiply probabilities unless you have independent events.
This assumes independence. Yeah, so we're capturing the one hop, the one hop frequency of the event. So yeah, you're right. This is effectively like this is like back of napkin machine learning, like a very, very naive statistical model that we're using here. And I'll touch on some of the merits and also the limitations.
So you're not trying to find a probability or anything, right? You're just trying to get a sense of, is this something that happens a lot, or is this something that happens rarely? If it happens rarely,
yeah. But yeah, no, these probabilities don't reflect the likelihood that this edge succeeds this edge or something like that, or other way around. So, a few more wrinkles here. We did want to account for the fact that some processes might have more connections than others. So in addition to calculating the frequency of source relationship destination tuples, we calculated the probability that a given vertex connects to anything on that relationship, and we put that in the denominator of this weight, just so that we can kind of control for the fan out of the graph. And we also normalized for the path. I want to briefly skip over that. So there were some complexities, but the high level idea was we calculated the frequency of each event, aggregated them together and attributed that to the alert as an anomaly score. So I want to show one other potential way that we could do this, and we'll see the results for both in a moment. I also mentioned earlier that if we're examining the provenance of these alerts, we might also see causal dependencies between multiple alerts. So we could use that as the basis for triage as well, but I did start off by ragging on these EDR systems, talking about how bad their signal-to-noise ratio was. So there might be sort of an issue there. So how can we denoise these alert streams in a way to create a more valuable signal? Well, I mentioned earlier, every single alert might be associated with some severity or confidence score. It might not be a good idea for us to just blindly add these numbers together because of the semantic gaps that my audience politely exposed, because of just the fact that the threat detector itself is noisy and unreliable. They're also associated with these MITRE ATT&CK annotations. And one of the cool things that MITRE ATT&CK does is it explains why an attacker would engage in the things that they're doing, which it calls tactics like initial access, execution, privilege escalation. And so we might expect that the false alerts that the threat detection system was firing would be kind of random or uniformly distributed, not sort of adhering to any sound tactical strategy here. Whereas true alert interdependencies, we might see the different sectors of the MITRE ATT&CK framework light up like a Christmas tree. And so given a function that lets us see the tactic associated with a given alert and its severity, what we essentially did was try to come up with an attack chain that maximized the total score for each tactic independently, and then we took the product of those. There's something that we did in this initial paper, which I think is a bad idea with the benefit of hindsight. In the original paper, we actually enforced the ordering between those different segments of the MITRE ATT&CK framework, like initial access needed to come before execution. And if we were using a chain where execution came first, that was invalid, so we would reject that. Basically kind of a misnomer, assuming that the tactics in the MITRE ATT&CK framework would be happening in sequence when that's often violated in practice. So we've thrown this out in previous, in subsequent work, and I didn't picture it here. And in addition to that, we also added a decay factor for when we see repeated alerts associated with the same tactic. So rather than only being able to count one alert associated with a tactic, we can kind of slowly, exponentially decay the contribution of repeated tactics. We've also started doing lateral movement tracing in these graphs as well. And so as we see alerts span multiple hosts, this gets more and more suspicious. So we've started, exponentially increasing the contribution of subsequent alerts. All right, so does any of this work? Two different papers, two different evaluations. Both of these were partnered in collaboration with industry security software vendors. So we were using their commercial threat detection products as the basis for evaluating these systems. The first with NEC, we were using a now defunct anomaly-based threat detection product, and then subsequently with Symantec, we were using their manually written detection analytic-based detection product. With NEC, the test bed was their entire Princeton office, so it was 200 machines, and the noise profile was all of the employees just going about their business on those machines. With Symantec, slightly more restrained, there was a 25 machine live machine test bed within Symantec Research Labs. And in both cases, different threat behaviors were injected into this background activity, causing a number of true positives and a far greater number of false positives in both cases. So for the event frequency approach, here is a ROC curve depicting the relationship between true positive rates and false positive rates for different score thresholds, right? And we saw that there was strong separation of these anomaly scores between true and false alerts, area under this curve of 0.95. So to actually turn this into an effective triage mechanism, we might want to specify some thresholds and say, okay, if something's above this threshold, we'll actually investigate. If it's below this threshold, we're going to throw it out. And for a threshold that allowed us to investigate every true alert, we found that 86% of the false alerts were immediately dismissible, so only about 14% confusion. With the alert interdependence approach, what we found was, first of all, I talked about the difficulty of correlating alerts together when we're using, potentially unreliable relationships. Like these things occurred on the same host, they occurred in the same hour. Obviously, the potential for spurious correlations were there, but in our case, we're actually using the causal relationships to determine how the group alerts together. So first, just sort of observing the efficacy of that. We went from almost 60,000 false alerts to just 700. There were 1,000 true alerts that were fired by the Symantec EDR, and that reduced to just 5 clusters of true alerts. So then when we go to look at the,
Very quickly, what's a TPG?
terminology that I didn't want to wade into, it's basically the graph that connects the alerts together, a tactical provenance graph. But I thought the figure was pretty, so I copied it over from my student's slide instead of updating it. Yeah.
I'm trying to understand the setting. So you got data, network traffic, or whatever data from researchers just going about their business, and then you took it offline and injected threats. Is that what you did?
Yeah, great question. So, whole other kettle of fish. Great questions. In NEC, they did what you said, where they injected the attacks after the fact, and there was a whole line of amazing work that this group was doing at the time, and this was the methodology they used in all of it. So potentially a little bit spurious, because rather than actually have it be a live attack engagement, they detonated some malware in a sandbox and then kind of like grafted it onto the logs after the fact. Nothing we're doing was anomaly based though. And so there wasn't a real learning mechanism here, so it's unlikely to have affected this result, but certainly the potential for artifacts to affect the result. This was a live attack engagement, and in particular, these two were part of the MITRE CITD attack evaluation framework. So MITRE hosts a attack engagement for enterprise security products once a year or so, and tries to create highly sophisticated simulations of these attackers. So that's particularly what they were doing.
So they actually injected attacks into their live network?
No, not into their live network, but the attacks were happening. This was a set of machines that were being used for research infrastructure. No, they weren't like, hey customers, by the way, we're going to attack you today.
That would be interesting.
Yeah, no, for sure. We've done something with Carbon Black more recently, where we did use live customer data to validate some of the approaches. Okay, so we saw the event frequency approach worked pretty well. We saw that the alert interdependence approach was doing a good job of correlating things. And then looking at the actual triage efficacy, what we found was that 98% of the false alert sequences, the TPGs, had a lower anomaly score than the minimum true attack TPG. So again, really strong separation between true triage scores and false triage scores, representing a 34x improvement in the signal-to-noise ratio of the system. So clearly, I don't think that either of these methodologies are necessarily like, yes, this is exactly how we should be doing this. I interpret these results as a broad indicator that doing this historical analysis of alerts is the path forward for denoising our threat detection products. Okay, so a couple discussion points. Adam, wouldn't all of your work be better and more relevant if you were using neural networks? And
Quantum.
yeah, and we are, yeah, well, no, thank you. And so one issue with that, we saw, my data sets were already being picked apart a second ago. So when we think about a general data scarcity problem for intrusion detection, very little agreement in terms of what a data set should even be, like what makes sort of an ideal benchmark when we're trying to determine whether this intrinsically adaptive, sophisticated adversary can be detected by a given product. The capacity for neural network-based mechanisms to learn is going to potentially result in a lot of overfitting and brittle, non-generalizable results. We also have this issue of explainability, right? So I wouldn't be able to say, yes, the neural network we threw this telemetry at learned that, the frequency of events or the relationship between alerts is the thing that's causing this stuff to work. So there's a lot of value in using these de-skilled approaches as scientists as opposed to engineers to determine, what about this data is, what structures exist within this data that can be used to solve this problem. We are doing a bunch of neural network-based intrusion detection, but not in this alert triage space because we only have a couple of thousand alert samples at a given time. If we look at the underlying event telemetry, which is orders of magnitude larger, it's a bit safer to do. We also found that doing this full historical analysis isn't always necessary to filter out the majority of false alarms. Picked a very similar talk to Carbon Black a while ago, and they said, that's awesome, that's way too expensive. Doing this historical analysis, we're never gonna do that. We've got, a Cadillac of this, trillions of events per second, infrastructure, this is too costly. So, the jury's out. I disagree, but in any event, we did collaborate with them to kind of make inferences about the provenance of an alert based just on the immediate context. And we found that just by looking at the command line that was used to start a program, it stands to reason that a series of events will lead to certain arguments in the command line. We found that we could actually reduce 83% of their global false alerts in real customer data using that approach. Yeah, go ahead.
Does this also work for Windows programs?
Yeah, this is the vast majority of this is Windows programs. Yeah, where all of that semantic gap stuff is even worse. And I only recently realized that Windows is vaguely inspired by microkernel architectures, right? So all of the stuff that's just a trapped to kernel in Linux is a visible interprocess correspondence in Windows. So all of those issues about fan out, about semantic gaps, far worse. And so, perhaps because of that, I was wondering, okay, now we're going to move into distributed tracing and lateral movement. And it's kind of this arms race between the noise, the imprecision of these graphs, and how strong this signal actually is. And we're actually finding that the signal is outpacing the noise in spite of those problems. We're developing new heuristics for tracing through windows. But yeah, there does appear even without having to re-architect what these systems are doing to provide more faithful telemetry streams, we can still do this in practical deployments and get a strong result out of it. All right, so awesome questions. I'm not exactly aware what time it is, but what time is it right now?
20 minutes.
12:38. That sounds good. No problem. All right, so I want to pivot a bit and now talk about, okay, here's how I'd like to improve these products. How are people currently reasoning about these products? And one of the answers to that is the MITRE ATT&CK framework. I mentioned these engagements that MITRE does to sort of see how the MITRE ATT&CK framework is being used by these commercial products. These products then immediately turn around and load their marketing materials with these insane brags like CrowdStrike achieves 99% detection coverage in the MITRE ATT&CK evaluations. And it's sort of become this hot new security metric. Anyone that's been doing security research long enough understands that like measuring security is really hard. So what are the
Advertising is not.
Yeah, advertising is much easier. What does it mean to cover the MITRE ATT&CK framework? So first of all, what is the MITRE ATT&CK framework? This is a grainy screen grab of what you see if you went to their website, and a quick overview like of how this knowledge base works. It's hierarchical. We have that set of tactics that I mentioned earlier that represent the high-level objectives of an attacker, kind of the why of the attack. Beneath each tactic, we have a set of techniques, which are strategies for achieving those objectives, the how of an attack, and then at the lowest level, which is in visible figure, we have procedures, which are specific implementations of those strategies that have been documented and confirmed in real-world threat intelligence. And so what we kind of have is, from this, documented threat intelligence and real-world threat groups, we end up with this sort of pyramid that's kind of documenting what attackers are doing and why they're doing it. So we have this rich hierarchy that, for God knows what reason, is most often butchered into TTP, which stands for tactic, technique, procedure. And this is my pet peeve that I try my best not to penalize papers for when I'm reviewing. But when people say TTP, they mean technique, this sort of middle tier of the general strategies attackers are using. So how does that map onto these products? Here's a couple more examples of manually written detection logic from different families of threat detection products. And as a reminder, all of these rules, in addition to other metadata, have annotations that attribute the high-level behavior to a tactic and a technique. So more broadly, sorry, I missed an animation, I guess. So that's what people are saying. When we have 65% coverage of MITRE ATT&CK, what we're saying is that we have a rule that is attributed with 65% of the techniques in MITRE ATT&CK. All right, so how are these products using the MITRE ATT&CK framework? We wanted to delve deeper. We sourced the threat detection rules from three major threat detection products, both Endpoint Detection and Security Indicator and Event Management, SIM, which is the software that's responsible for aggregating all the different telemetry streams, and it also does threat detection. So we had thousands of rules that were annotated with the MITRE ATT&CK framework, and our research questions were, how is attack integrated into these detection analytics? Spoilers, the products don't fully cover the MITRE ATT&CK framework in spite of some of those headlines. Why is it that the products aren't fully covering the MITRE ATT&CK framework? And how consistently is the MITRE ATT&CK framework being applied across different analysts and different vendors? So first, we just visualized the annotations by product. Y-axis here shows each tactic in the MITRE ATT&CK framework. X-axis shows the number of techniques that are covered. And our green dots here show the total number of possible techniques in the MITRE ATT&CK framework for that tactic. And so we can see there's a little bit of variance product by product in terms of how much coverage we can see. The gap between a given product and the green dot shows the number of techniques under a given tactic that weren't covered. If we take the union of all the different products, we find that we still don't have full coverage of the MITRE ATT&CK framework. We do get there for a couple of the tactics, but then there's others where the gap is still noticeable. So coverage across all products is still far from 100%. These are, pretty major products. So we're not able to test all products in the universe simultaneously, but yeah.
So I wonder what is it about privilege escalation that everyone is doing so well? That's so easy to detect?
Yeah.
Or is there just not enough tactics in the MITRE framework?
So let me snooze that for just a few minutes, okay? Great question though. It's actually a little bit worse than that. I mentioned earlier, we have alerts being fired with severity 1, severity 2. No one is ever going to have enough time to investigate those alerts. So how much value are they really providing? If we start filtering the alerts based on sort of, are they greater than medium level severity or confidence? The scores associated vary by product. Or if it's the upper 25% in terms of that score value, how does coverage change? And so we can see in cases of things like Splunk, the coverage drops quite dramatically to as low as 25% coverage for high severity, immediate react to this detections. This doesn't mean that Splunk is doing something, it doesn't necessarily mean that Splunk is juicing their results here, right? Because it could just be that these detections genuinely aren't that severe. But clearly there's an incentive for those marketing materials to provide strong coverage, so it's worth considering. Yeah.
They're only listing one side of the detection, right? They're not telling you how much false positives they're getting.
Yeah, a couple of the products will qualitatively describe false positive conditions in the other metadata. But yeah,
100% detection.
it's aside from data sets where we're observing the threat detection behavior, so we've created a couple of these data sets now, and the most I can say is that okay, the attack is the attack, and we can talk about how sexy the attack is, but in terms of the noise profile, this accurately reflects what 10 computer security researchers at a major Midwestern university were doing for a week in May 2024. So it's kind of, it's very difficult to sort of come up with, to be certain that we're doing something representative in terms of the signal noise ratio of products or analytics. We've identified this perverse incentive where attack coverage is used to sell products, and we've also seen that if we start looking at the rules that are actually being used, coverage is not looking great. Why weren't these products covering more of the attack framework? There were 53 techniques that none of the products implemented, so we had 3 coders go into the MITRE attack framework and try to figure out why that was the case. We identified a number of explanations, the top 3 being ineffective detection method. The behavior wasn't related to the target infrastructure, or detection would require knowledge of deployment specific constraints. So some examples the MITRE attack framework often explicitly mentions that it's hard to detect this thing. Internet scanning of remote infrastructure isn't something that I can detect in my product, in my deployments. Also in the reconnaissance tactic, there's the attacker might crawl Facebook in order to identify who works at your company. Well, great, I can't see that, right? So limited visibility. Stealing, access tokens for a particular application would be something my own security operations center would need to write for my application. And so I think I'll pick up your question here. One of the issues with all of this is, for all of its many strengths, the MITRE attack framework is a qualitative, fuzzy attempt to systematize what attackers are doing. There's nothing uniform or consistent about how the MITRE attack framework works from technique to technique. So I think the answer to your question of why are we crushing it on persistence, probably if we looked at those techniques, we'd see that they don't fall victim to any of these pitfalls. Some of the techniques are bewilderingly specific, like there's a technique associated with abusing LSASS, the Windows service. And so one would think, oh, it's kind of weird that this is a technique that sounds, you're talking about a specific program that should be an implementation level detail. And so one of the things that we do in this paper is identify sort of community complaints about how MITRE attacks being used to provide evidence for the fact that, like, yeah, this isn't sort of this, comprehensive, systematic catalog the way that people are kind of confusing it to be. So our last research question here was, how consistently are people using the MITRE attack framework? We identified a subset of our rules where every single product, or at least two products, were trying to detect the exact same thing. Like we used keyword searches, we found, references to this CVE, to this threat group, etc. And so we looked at the techniques that were attributed to those rules, right? And so, from these Venn diagrams here, you can hopefully see that there's a fair amount of healthy disagreement about which techniques are associated with these specific threats, even for a CVE, which is not going to be like a rich catalog of multiple behaviors. It's one specific thing. In the case of some of the more sophisticated threat groups, we can see there's actually, no overlap between the techniques that these three different products families were using. So even when detecting the same threat, products don't consistently use the same attack techniques to describe it. This is not saying that the analysts are stupid. It's saying that reasonable people can disagree. Here's an example of two detections, one for Elastic and one for Splunk, related to named pipe impersonation. We confirmed that there exists a single command line that could cause both detections to fire. Elastic says this is access token manipulation. Splunk says it's commanded scripting or modifying a system process, and they're all right. Yeah, they're all right. In rarer cases, we did find examples where the annotations might lead to different conclusions. So this namespace lookup activity, Elastic says it's command and control. Splunk says it's exfiltration. Maybe that affects our incident response plan. But these instances were much more rare. Most of the time, a coherent story still emerged, but if we're talking about coverage, like either you detect this technique or you don't, that's not, that nuance isn't captured by that metric. So to sort of wrap this up, don't jump and go. If no product offers 100% coverage of the attack framework, and if we've shown that it's not possible, it will never happen, that a product can certainly offer like high fidelity detections for every technique in the attack framework. And if the products are making inconsistent use of the attack framework, in truth, none of this was necessary for me to craft this argument. I want to go back here. When we talked about how these annotations are happening, this detection logic is procedural. It's the bottom level of the MITRE attack framework. So we're saying in this detection, I know that there's at least one implementation of this technique that I'm able to detect. But when we say, the moment that we write a single rule, this coverage metric is saying this entire space of attack behavior is covered. So coverage of a technique actually means coverage of a single procedure, and that's not reflected. And that, in fact, was my, my soapbox rant that motivated this study. So given that, even though, the products are also marketing themselves based on a fundamental misunderstanding or misrepresentation of the attack framework, while MITRE attack is amazing, the analysts are amazing, individual, people in the ecosystem are making rational decisions, it's quite clear that, this metric itself is not an effective security metric. We disclosed these results to the not the affected companies. We shared these results as best we could with the companies, had some longer conversations with Carbon Black since we knew the right people there. And I sort of said this is all the marketing people's fault. they were actually really excited about this result because in addition to doing this sort of misrepresentative, press releases, they were also peeved that other evaluators in the ecosystem were marking down Carbon Black for their use of MITRE ATT&CK framework. They knew that these problems existed. So like Forrester, Gartner, people that do these like product ecosystem evaluations, they don't necessarily like Carbon Black. And so the marketers were thinking, oh, maybe we can use this to improve our, Gartner score or something like that. How am I doing on time now?
5 more minutes.
5 more minutes? That sounds good. So I wanted to briefly discuss some of the things that we're working on in follow-up work. The work was also well received by MITRE. No one was mad at us, so that was nice. The lead author on this, Apurva, went off and did an internship with MITRE this past summer. One thing that she worked on was this self-assessment that MITRE releases so that organizations can assess their security readiness. In response to this work, they kind of diminished that attack coverage component of their survey, so that was a nice outcome. We're now designing an assessment of their assessments with their help to try to understand, again, kind of building on this result, how do organizations evaluate their own security and how do they reason about it? And so we're optimistic about that. Another cool product or program that they're working on is clearly not all detection analytics are created equally. Going back to the first questions in this talk, if you're raising a detection based on like a hash value, an antivirus product, I recompile once and your detection is no longer workable. If you're matching against maybe an IP address or a domain name, those are pretty easy for an attacker to re-roll, right? This is all kind of captured in this thing called the pyramid of pain, which is basically claiming that, if we craft our analytics to use things at the higher levels of the pyramid, going all the way up to TTPs, then the detection rules will be more adversarially robust. And so MITRE has a program called Summiting the Pyramid, where they are trying to evaluate the quality of rules. It's fully manual. It's been around for like 4 years. They've scored 100 rules total. So there's a lot of manual labor going into this process. We actually think we can automate some of it. So we're working with them to try to do that as well. Going back to sort of the first half of the talk, we are, one of my students, against my wishes, co-founded a company with me and is trying to commercialize some of this alert triage stuff. So we actually have a prototype. We're using live data. We're able to surface the causal relationships between alerts and then do scoring on that. This is another one of those sophisticated attack simulations that MITRE put out. One of the interesting pieces of customer feedback we've received is here's the raw provenance graph. So be surprised to hear that people don't love this. Obviously, it's a little bit small on the screen, but I think the general noise is reflected. So increasingly, we're thinking, okay, only the most senior analysts are going to be able to make sense of the information on this low-level graph. Maybe what data provenance is an engine that powers higher-level analytics, like the identifying and correlating alerts, like making sure that our AI agents are hallucinating by providing them a denoised representation of what's happening in the system, so on and so forth. All right, thank you so much for your time. Here's a few of the awesome students that did all this work. Unfortunately, since so much of the work was in partnership with companies who technically own the results, I don't have a ton of specific source code that I can share, but we have re-implemented a few of these things, so if people need a copy of this, talk to me and share it. Thanks for your time.
Questions?
Why is it so cold in the room?
Because the heat pumps are really efficient. I don't know. I have one.
Yeah.
On your last slide, you started your talk with it's a bad idea to just add together the alert importances, and here you have a 12 out of 10. which is the sum of your forward initial.
Where's the 12 out of 10?
Very high severity, right
Good
under the.
eyesight.
Ugh. Yeah. Yeah, I think my student was, so they were, I know what happens. The number just goes up. And at some point, we overbit on customer discovery feedback that the number needs to be normalized. So what this is here is they picked an arbitrary value. We changed the product so that the discriminatory power increased, and now we're grading. This one goes to 11. Yeah.
So the nodes in this graph are subjects and objects.
Yeah, so
And the
processes,
edges are events.
network files, registry keys, yeah, data entities.
So the severity is assigned to what exactly?
Yeah, the severity is, so here's a subset of the alerts that graph fired. All of these alerts are associated with severities. And so you can kind of see the mapping here. So this is a high severity alert, which is right, it's red. If we go over to this graph, it's this program that's associated with that.
Shouldn't the severity be assigned to a path in the graph?
In this case, the severity is the entire graph. So we're taking all of the causally linked alerts and assigning an aggregate score.
Cool.
Yeah, a little bit of validation that we can actually, admittedly this is too noisy, but this is real data on Windows. You know, we have enough tricks that we can denoise it enough to get a pretty good score. Yeah.
Sweet.